Good. So, just in case, I don't know if you saw the announcement that, but you can check the information about the exam on the website. The practice problems, exams were already posted on the MyLab. So, uh, well, it is online for us because everything is online. Yes. Uh, it it's yeah, it is up until 15/7. So essentially, let me see if I just need to share my. Uh, let's see if this. Okay. Yeah. So today we are doing 15/5, which is about triple integrals in Cartesian coordinates. So now there's a section which we're skipping, which is 15/6, because that's just like about applications. So I mean, you can read it if you're interested. It's like about how to find like moments of inertia and other things. It you just set up like a triple integral. So we're skipping 15/6, and so and then 15/7, which would be the last topic for the exam. It's like that actually takes a little bit more time because it really should be like 2 sections on the book, because that one is cylindrical and spherical coordinates. So each of those topics probably deserves its own lecture. So I think we'll be done with the material by next Monday. Yeah. So kind of that's more or less the plan. So we do have time, but and I suppose there are 7 practice. There are like 5 practice exams on MyLab, plus 2 on PDF that you can find on the website where the announcement was posted about on the exam. So. But yeah, like for us, all the exams will be online, so you don't need to worry about that. Yeah, so as I was saying, today we're going to talk about triple integrals. So essentially, what I need to explain is, what do you do when you think like this? Where here, now the function is like a function of 3 variables, right? So this is like function of 3 variables. And now the region R is really like the place where the integration is occurring is some subset of the of 3-dimensional space. So here it would be like R. This is some region of 3D space. So like maybe this is R. Okay, so so essentially, like doing these integrals is that the different double integral. The new thing is like now you have to find bounds for like regions in 3D space. So up to this point, like every drawing that was sort of being done on the XY plane, and now you have to introduce a third axis. But just to like mention, like you can still think of this integral. The easiest way to think about this integral is as a sum of quantities times volume. So there's still like this interpretation, like in terms of sums, like Riemann sums, if you want the full name, where you think of this as like literally adding up products of the involving the function and some tiny piece of volume. So the piece of volume here is like, think of this as a mini box. So this is like dV. So dV is like a piece of volume, tiny volume. Okay, and so it is similar to before. Where volume, like in this case, could be dz dy dx, or it could also be dz dx dy, or it could also be well, let me put it like, let me write it here because there are actually 6 possibilities. So dv would be, could be dz dy dx. This is actually, I'm writing this one first. Well, it's not really like it's not really like a shrunk version of R, because R can be like you know, it's like an asteroid, so it's not really like, it's very wavy, it's very curved. So it's not just that you, like, you know, those movies where you just shrink everyone by the same, in the same proportions. You're just thinking of like making, let me see if I, maybe there's a GeoGebra animation for this.
It was making sense where you were going with it.
Yeah, it is not. I'm just trying to see if like the Riemann sums appear here.
Oh, okay. I think if we're going to break it down like we did with the 2-dimensional integrals, then I'm guessing they're going to do an integral with respect to x, y, and z.
Right.
And that's why the box makes sense.
Yeah, like, so for example, like, let me just draw the picture here. Like when you had, imagine you had like this weird region on the XY plane, you still thought of like maybe chopping it this way, right? Into a bunch of mini rectangles, right? But they and near the edge, okay, this near the edge doesn't look like a rectangle, but you can, like, if you were to zoom, you know, you start zooming and you keep chopping, and then you get more like a more mini rectangle. So you really keep chopping forever. That's the whole point of like the Riemann sum being like some sort of limit to the, like, you need to take the limit of the sums to get the integral. But you see, like, if you just choose like a random rectangle here, its shape has nothing to do with like the shape of the exterior. So it's something like analogous to what we're about to do here, where, like, you know, you're sort of going to chop this 3D picture, and so like you get like tiny boxes of the region, right? Or like, you know, like when people like they chop a cucumber, zucchini, like, you know, they look like mini box, like, you know, minis, like boxes. They don't, like, you don't get like a zucchini, a mini zucchini, right? When you cubes, that's a, yeah, that was the word I was going for. I don't know why I forgot it. Yeah, but when you chop something, like, you get cubes, kind of, right? You don't get like like, you know, like the same shape that you started with. So so just imagine like making up this region out of tiny boxes or cubes. So what I was saying is that I don't know if someone was going to speak. It's just like what I was saying is that, right, instead of like just doing dy dx or dx dy, now you can do it, you have to add like a third variable. So it's like dc dy dx. But like something similar will happen where really it doesn't matter which order of integration you do for the actual, for finding the bounds. I mean, for finding the integral. So you could like change, like, for example, x and y, but by the same logic, there's no reason why dz would need to go first. So you could write something something like dy dc dx, or you could write something like dy dx dc. And by the same logic, still like this can keep going because dx could be the first one. So dx dy dz, or dx dc dy. So there are really like 6 ways to do the integ, like, you know, that's the difference between 2 times 1, right? For double integral, it was 2 times 1, and now it's 3 times 2 times 1, because in the first slot you can put like one of the variables, and then in the middle you put you have like one fewer option, and then at the last one you just like it's completely determined. So there are like 6 ways in which you can do the integrals, but really the first one I just wrote is like the most common order of integration. So I'll start explaining how to do it this way. And they will give you the same value. That's the point. Yeah. In regardless of the 6 ways you could do this, they will always give you the same. Okay. So we'll start with this one. Okay. And by the way, like again, if you wanted to think in these terms, when you do a triple integral, like if you actually thought of this as being like an applied problem where like things come with units, right? So there would be some units for the triple integral. So, and so the units of this would be, oh yeah, they're very quite common. Yes. I'll give some examples. This would be the units of f times the units times units of volume, or times volume. So like for example, like there are many cases. Like what like the easiest case would be like here. Let me just put it like this, like some examples. Like imagine that flux actually will appear later in the course. That one is I mean, it's a little bit different from the integrals we have been doing, but it's called like a surface integral. But like again, like imagine if this were like some asteroid floating in space. So like F is here like the, you know, like the mass per unit volume, which is another name for saying density, right? So what would be the triple integral of f dv, right? It would be the integral of the density function. So what would you get when you get the integrated the density function? Well, at least if you just look by in terms of the units, the units of this, like, you know, This has units of mass over volume times volume. So this has units of mass, right? So in fact, this gives you the total mass of the planet or the asteroid, right? Is that making sense?
Professor,
Yes.
when we did double integrals, the order of integration mattered, right?
I mean, it matters. I mean, in the sense that once you like, if you want to do it in the if you want to change the order, you have to change the bounds, right? But if you change the bounds properly, you will find the same answer, right?
Okay, and it's the same here.
Yeah. It's the same. I mean, you can do any order of integration, but if you choose a particular order, then you just have to find like the corresponding bounds, right? So the bounds do change depending on the order that you choose. Is that
Okay.
yeah?
Yeah, that makes sense.
But like it should come to be the same answer, yeah. After you have made the appropriate changes in bounds, yeah.
Okay, cool. Thanks.
Yeah, sure, no problem. And like for example, there's this like Newton's Shell's theorem. I don't, or I mean, I think it has different names, but say imagine that you wanted to like for say find the force that a planet like the Earth exerts on a satellite, right? So like one way to think about it is that you chop the planet into tiny pieces. So there's like some mass, little mass dm here, and it's exerting some force on the satellite, which has some mass m. I should put like yeah. Let me put it. Let's put it. Okay, that's fine. And you know, then like by Newton's law, I mean, roughly the force is like G m times dm over the distance squared. You could call this distance d squared, right? That's in like, well, I mean, there could be a minus sign depending on how you like it, strictly speaking. But like if you just wanted to find the magnitude of the force, right? dm is just like a little piece of volume, right? So this is like, but since it's a sorry, it's a tiny mass, so this is really like doing like a very small contribution of force. Like let's call this like let's call this r just for 6. I mean, it's not the same r as in polar coordinates, so it could be confusing, but it's like, and then the total force, like that's all that I'm trying to say. The total force would be like sort of like the sum of all the contributions of tiny forces. So the total force should be like the triple integral of these forces. So it would be some triple integral of g m dm over r squared. But then like, I mean, if you take like a physics class, you'll see that dm is like the density times dv, where rho here is like the density function. So if you want to find like the total force like a body exerts, you have to do like a triple integral, basically, something like that. And again, like if you go to like section 15.6, that's kind of the stuff that they discuss in the book, which is the section we're skipping, but you can read it if you want to see how the triple integrals are used. But they get used, you know, like in this way, also if you want to find moments of inertia and other things. Okay, so but yeah, but for us, like what you're supposed to learn in this class is how to compute them, and then in different classes you're supposed to learn like what they mean, right? So but like that's sort of like the stuff that they're related to. So let me tell you like the rules for finding these integrals. Like, let's say you wanted to do this order. And again, like I'm starting here because this is really like 90% of the time, this is like the order of integration that we will use most like commonly. Like so like if you see something like this, what this is going to mean, we are about to do an example. Like the thing that this means is that you're going to start integrating first with respect to the variable z, okay? And so when you integrate with respect to the variable z, I don't know if you remember, like if you had no z and you had the y dx, we use like arrows parallel to the y-axis, right? Now what we're going to do is like use arrows parallel to the z-axis. So here we're going to use arrows or lines. Okay. And so like it's the same, that's a good thing. It's essentially the same idea as before. So what we're going to put here is like the equation of this, like this is the difference, like the equation where the arrows enter, right? So this is like the equation. It's like the equation of some surface essentially. So let me put it like this, surface. And this will be like a function of x and y. So this would be like the equation in terms of x and y. And this, the last one will be like the one on top will be the equation of the surface where the arrows exit. So like what I'm trying to say is that it is the same. It's just that instead of using arrows parallel to the y-axis or the x-axis, now you use arrows parallel to the z-axis. Okay. And then for these two, you basically like what you do is you look at the shadow, like the shadow or projection this region makes on the XY plane. Okay. And you find the bounce using like, and then you find the bounce in the same way as before. And then you find the bounce for the shadow as a double integral. So let's see. I will just giving you a second to copy it, and then I'm about to do an example. Okay. Let's do an example. So let's say you wanted to find the bounds. Well, or even like, yeah. Where the region it's a tetrahedron. Okay. So let me well, in this case, for example, you wouldn't like in this you would integrate with respect to z first, right? Because dz appears first. So you would have to put like z squared over 2, right? But the problem is that we don't know what bounds to use. Like that's what we're about to determine, right? So it is not, there are like a couple which are not that difficult. So I don't know, like, x equals 0. What's x equals 0? That's the equation of a plane, right? Y equals 0, or like, let me, sorry, let me do z equals 0. Z equals 0 is the equation of the other plane. And then y equals 0 is the equation of the remaining plane. Is that making so far so good? Is this making sense? So up to this point, it is as if you had just taken the corner of one of your rooms, right? And you had colored each side of that, like at that corner with a different color. You know, like you have like two walls and the floor, and you have colored each of those with a different color. Is that making sense? But you see, like the way it is so far, like this is, by the way, like the way in which it is written so far, you know, it's just like some sort of there's no, you can escape through this room, right? Because you know, you just have like the floor and then two walls, but so you can enter and leave without issues, right? So in a sense, that's not like a region that's finite, because you have to add either more walls or something else to close it up, right? So that's where this fourth plane is going to come in. So let's think about the equation of this plane. In fact, I don't know if you remember, what's the normal vector to this plane? Well, remember it was a vector. So, but you're getting there. Yeah, yeah. 1, 1, 1. Good. Now, one way to think about this plane, like, which is like in practice how you use it for like yes, and kind of it is close, yes, but only for one of the variables. One way to think about drawing this plane, like the way in which this is usually done, is by just setting two of the variables equal at a time, so that you get like the intersections with the x, y, and z axis. So, for example, along the x-axis, you know, y and z are 0. So if y and z are 0, what is the value for x? X has to be 1, right? So this is the point 1, 0, 1, 1, 0, 0, right? And then along the y-axis, x and z are both 0. So you get the point 0, 1, 0. And along the z-axis, you see x and y are both 0. So if x and y are both 0, you get 0, 0, 1. Right, so those are like the places where the plane hits the axis. Is that making sense?
So the normal vector kind of points towards the origin, right? And the plane is slanted.
Right, it's slanted, correct. That's what I'm trying to, yes. So what you can do is sort of, you know, drawing it this way, and then like the normal vector is 1, 0, 1, 1, 1. So this is like a way to think about it, right? Because as you said, it's slanted. But like in terms of the picture, I mean, it is like you could have started just by drawing the vector 1, 1, 1, and then try to find draw like a piece of paper that's perpendicular to that vector. But like the easiest way to do it is just like by drawing like the 3 points of like intersection, which like the axis, and then like just by like joining the like the corresponding points with some lines. And so like what are you seeing here is like the part of the plane that's trapped inside the three walls. Like that's what I'm like this is what this picture represents. Is that making sense? Like, let's go to GeoGebra. I think this will help. Can everyone see it? So well, if you normalize it, yes. I mean, normal vector does not need to have like unit norm, but the one that you're writing is also a normal vector. There are many normal vectors because you can always multiply them. Does everyone see the plane here? So this is the plane that I drew in purple on like the x plus y plus z plane that I drew here in purple on the iPad. So if you think about it, like the points like 1, 0, 0, 0, 1, 0, and 0, 0, 1 are these 3 points that I drew from the intersections, right? So they're like the points that you see here. And so basically what we're doing, I mean, we're sort of we're building this like one of these modern houses, you know, where like the roof is not parallel to the XY plane. We're just building a modern house where like, you know, the roof is sort of like tilted or slanted. So like I mean, if it's really like a roof, I mean, if it's really like a house, you have to add like the other like you know, the walls. So right, like I'm adding x equals 0, and for x equals 0, I use yellow. You see, like now we have like, you see, like we're trapping something inside like some sort of box. And then you can put z equals 0. And when you put z equals 0, you're almost there. Z equals 0, I use color green. And so you see, like we have to close it up, and for closing it up, I just have to add like the other plane, which is y equals 0. And when I put y equals 0, I'll put it here. And with y equals 0, I use the color orange. So here it is. So everyone, like, can everyone see the 3D region? It's sort of like the stuff that's like where the roof is the purple stuff, the floor is the green plane, and then the lateral walls are like the orange one and the yellow one. Is that making sense? Good.
Then when we're integrating, we're finding little cubes inside of that.
Yeah, exactly. It is
Okay.
like, I mean, it is like when you give little kids to, you know, play with, right? Like where you give a bunch of them cubes and they have to place them in a container. So imagine just starting to fill in this 3D region by tiny cubes, right? So yeah. And just like making the point that you should think like, you know, if someone were trapped inside this region, like they would see like the roof to be the purple one. It's just like it was like tilted, right? It was not just like, again, like it's like a modernist like architecture design, because typically you may see those like these days like in more modern buildings, or like maybe it's not, it doesn't go all the way down to the floor, the roof, but it is not parallel to the floor.
The bounds of the z arrows, what you said that they should be parallel to the z-axis, right?
Right.
So then would they be going from the floor to the slanted roof?
Exactly, that's the idea. So let me, in fact, I mean, like in this picture, the crucial player is like the slanted plane, because the others you once kind of sort of figure out where they are located. So let me do like a better picture where I'm just drawing, like I'm emphasizing the purple plane. Right, and then the idea here is, yes, as you were saying, to use like arrows that are parallel to the z-axis, and they will look something like this. Like they start at different points. You see, they all sort of pierce through the floor, right? It's almost like the definition of what floor means, right? So they all enter through the floor, but they exit through the roof, which is the plane, right? So those are more or less the arrows that we see here. Is that making sense? So so what's the equation of, like, again, when like you're putting the bounds, and then let me put here dy dx. So when you're
Then
putting
the arrows would go from 0 to that plane, but the plane we need to have it in terms of x and y.
correct.
So then the z would be on the other side.
Right. So they all enter through the XY plane, right? Through the green one. But the equation of the green one was just z equals 0, right? So you put z equals 0 here. And they all exit through the purple one. But right, as you were saying, the purple one is like, really the equation was x plus y plus z equals 1, which is the same as z equals 1 minus x minus y. So you put here z equals 1 minus x minus y. Is that making sense? So those are the bounds for z, right? And then the bounds for x and y, what you sort of imagine is that you just imagine you just painted the roof, right? So the paint is fresh. And then like you used a lot of paint, and so you start seeing drops of paint fell, like, you know, they start falling down because of gravity. So basically what you have to find out is like the shadow, or what gets colored on the XY plane, right? And so you'll get something colored on the XY plane, and that's essentially like this triangle that you see here. So that's sort of like the shadow that the 3D region makes on the plane. Is that making sense? So this is the shadow. Is that okay? And then you can, like, the point is that you can analyze the shadow as its own picture if you want to see it more clearly. So you can draw like just the shadow here. And so the shadow should be like this thing. Is that okay? So remember, this was like one, there's a one
It
here.
would be like an equation of a line with a
Yeah.
negative slope.
Correct. Now you have to find exactly what's the equation of the hypotenuse, like in this case. Well, it's actually x plus y equals 1, right? And then like, if you want to use dy dx as the order of integration, like what I'm trying to say is that now you have reduced the problem to finding the bounds, like for the double integrals that you know from before. So for the order dy dx, you have to use arrows which are parallel to the y-axis. And so they go from y equals 0 to y equals 1 minus x. Is that okay? And then x just goes from 0 to 1. Is that making sense? So those are the bounds for in triple integrals for this order of integration.
So y plus x plus z is always going to equal 1?
Oh, well, in this particular example, right, you could have done a different plane where like the coefficients were different, right? In fact, if you want, we can do it like, let me do it, another plane problem, but with different coefficients. And maybe this will be more useful. But yeah, like this was more like an accident than anything else. Like, let me see. Yeah, I'll do an example. And the next one that I'm going to do is with a different plane. So let's say that now it's the same problem, but now with the plane. Let's say the equation was 2x plus y plus 6z equals 12, right? So it's that now the coefficients are not all equal to 1, right? And it's not being equal to 1 also.
Oh, okay, thank you.
Yeah, and now we're going to use, like, just to spice things up, we're going to use the order dy dz dx. Okay. So we're moving things around just to, you know, it's easier to explain how to do it in different orders of integration just by doing like an example. So exactly, if you want to draw this plane, you have to draw like the points where it hits the x, y, and z axis. So along the x-axis, y and z are 0, so you get 2x equals 12, so x equals 0, x equals 6. Along the y-axis, x and z are 0, so you get y equals 12, so this is the point 0, 12, 0. And along z-axis, x and y are 0, so you get 6z equals 12, so c equals 2, so you get 0, 0, 2. Is that making sense? But you see, it's not that different. Yeah, so like if you want to find like the intersection with the axis, you just set two of the variables equal to 0 at a time. So for example, along the x-axis, y and z are 0, right? So if y and z are 0, you get, let me write it on the chat. You get 2x equals 12, so x equals 6. Is that making sense? And then, you know, for the other ones, it's similar. You get like then y equals 12, and then you get 6z equals 12, so z equals 2. And so that's how I found these 3 points. Is that okay? Good. And again, you still draw the same plane as before. So the picture hasn't changed qualitatively that much. But now, like, the interesting thing is that, and again, this was the plane 2x plus y plus 6, 6, 12. So that's the same plane, but now the difference is that I asked you a different order of integration. So now I'm asking you to do this thing. using dy, dz, dx. Oops. Excellent, right? But like, just think about what this means. Like, it is the same from before. Like, now you're using arrows which are parallel to the y-axis. So now it's sort of, think of it as you inverted like the gravitational field. So now up and down have just been reversed, have like changed their meanings. So now you're using arrows parallel to the y-axis. Can everyone picture them? So they sort of like they sort of start from like, actually they enter through this like yellow triangle. Like they enter through this side of the wall. I don't know if I use the same color here. Oh yeah, kind of. It has been with orange, so I can do it with orange. Now the arrows, like, since they're parallel to the y-axis, they enter through that wall, and they all exit still through the roof, which is the equation of the plane. So, right, so the idea would be that the bounds for y, this is the xz plane, so that's when y equals 0. And they exit through the purple equation, but now you have to think of the purple equation as a function of x and z. So it's y equals 12 minus 2x minus 6z. Is that okay? Is that making sense? And then for finding the bounds for z and x, what you have to look is like at the shadow, right? But now the shadow is with respect to y, because that's like, that's sort of like the direction of the arrows that we used. So the shadow that this 3D region makes is now this like, this yellow orange triangle that I colored here. So you have to draw that triangle on the zx plane, or xz plane, however you want to call that one. So here you have the point 2, and here you have 6. So now you're drawing this triangle. So this is the one that you get. This is what I color here in orange. And what's the equation of this line? Yes. Which secretly is the one that you find if you take y to be 0 in the equation of the plane. So this is really the equation 2x plus 6z equals 12. But if you solve for z, that's the same as saying z equals 2 minus, minus 1/3 of x, right? Is it well, there are two ways to do this. Like you have 2 points, right? Because you have 2 points on the on this plane, so you can find the the equation of the line just by the slope intercept form. So that's one option. And or you could have started from the equation of the plane and set y to be 0. And so you get 2x plus 6z equals 12, and then you solve for z. So there are two ways to get it, but both would be fine. Is that making sense? And then, well, yeah, I think you're integrating, but let's just finish. Like, it's a kind of ugly, nasty integral, so I'm not going to try to do it here. But let's try to just finish finding the bounds. So you see, like the remaining order that is the z dx. So that means that you have to use arrows parallel to the z-axis. So you put here z equals 0. And then the last one is x goes from 0 to 6. Is that making sense? Any questions about this? Well, 6, just because that was like in this triangle the value for x. This because this is where like the this hits when z, like this line hits the x-axis when z equals 0. So when z equals 0, you find that x equals 6. Because you get 0 equals 2 minus 1/3 of x. And so that means that x has to be 6. I wrote it on the chat. Is that making sense? Okay, let's do one that's a little bit more complicated. So let's try to find the bounds for, let me write like this here. And here R is the region. I don't know if you have seen this word octant before. What first octant means? It's like saying first quadrant in the XY plane. So first octant just means that X, Y, and Z are all positive, right? So let me show you the picture first in GeoGebra, and then I will find the bounds.
Go back to the PDF for just 1 second.
Yes, let's see. This one.
Thank you.
That's right. So okay, let me zoom. Let me go. Okay, kind of. Okay, let me show you the picture in chat. So you have the sphere, right? So well, the first thing that I'm saying is that we're not going to look at all the sphere. We're just going to look at all the sphere, like the part of the sphere which is in the first octant. So the first octant is where x, y, and z are positive. So it's like 1/8 of the sphere, right? Like, so we're looking at the stuff of the sphere at the interior of the sphere in the first octant. Okay. And then we have the plane z equals y. Right? Which is this one. And so if you see what's going on is that there's some stuff, there's some part of the sphere, right? You see there's some region between the plane and the sphere. So in a sense, like now the plane works as the floor and the sphere is like some sort of roof. Is this clear? So
Like if you had a cake pop and you took a slice of it.
Right, exactly. Yeah. So it, like, I'm referring to this stuff between the sphere and the plane. The one that I'm using with my pointer.
Quick question. Can there be a case where we say only have to find a region within a sphere that is like a triangle inside of a sphere, and we need to kind of see what the projection of that is onto the sphere and find the volume within that? Would that be a case?
Well, I mean, I suppose like you mean like I guess it depends on what you mean like by the triangle. It's
Like say instead of that plane, you had a triangle in there, so that way not the entire kind of sphere goes.
Yeah, that would, I think, will require, like, it's similar, it would be similar to those triple integrals where you sort of end up breaking the it's more complicated because, like, if I'm getting what you're saying, you know, the triangle will require you to split the region into separate triple integrals. So
yep,
it's not going to, yeah, like something like that is like, I don't think if it's like without a picture being provided, I don't think that's something like yeah, I think I see what you yeah, it's like a bit too complicated. Yeah. So okay, but like this was just to sort of show you the idea of like how this is supposed to look. So let's try to draw it on the iPad. So what you can draw on the iPad is like, well, you should like, you don't have to draw like an entire sphere because you just care about the part of the sphere which is on the first octant. So you can just like, the easiest thing to draw here is something like this. Yeah, and hopefully this gives you like an idea of the sphere itself. Okay, so that's sort of like the sphere or the part of the sphere that you care about. And then how do you draw the equation z equals y? So to draw that equation, what you can do is like, what is z equals y on the yz plane? Is the equation of a line, right? So you draw like a line here. And then you just move this line around along the z-axis. And let me tilt it a little bit more. So you see, it's almost as if you were drawing like copies of the line z equals y along the z-axis. Oops. Well, so that's roughly how the sorry, along the x-axis. Yeah. Right, like, so you have z equals y, which is a 45-degree line on the x on the yz plane, and then you just move that one along the x-axis. Sorry. Is that making sense? So the stuff that we care about is sort of like the stuff between this purple plane and the top of the sphere, right? Like, you know, this part of the sphere. So all of this, like, let me like, I want this coloring will disappear, but this is all the stuff that we care about, basically. Okay. So let's see let's try to find the bounds for z. So for the bounds for z, again, you have to draw arrows which are parallel to the z-axis. So if you draw arrows which are parallel to the z-axis, you get arrows like this. Right? Can everyone visualize them? And so where are the through which equation do the arrows enter the region? Z equals y, right. They enter through the plane, which has had equation z equals y. Good. And through which equation do they exit the region? They exit through where? Through the sphere, but now we need the sphere in terms of z. So the equation of the sphere in terms of z is 1 minus x squared minus y squared. Is that making sense? So far, so good?
So then for the X and Y part, we would be looking at the shadow of the sphere or the shadow of the plane, the purple plane.
The shadow of, it's the shadow of the region, and the region is the stuff between the sphere and the plane, right? So you
Okay.
know, which
That's funny.
so it's that one is complicated, right? Here, like, the thing is, like, think of you're looking at think of the sphere as an orange, right? So you slice the orange with a piece of paper, right? And then what's going to happen is that as you know, this slice sort of exit the sphere at different points. So essentially, like, let me delete some arrows, sorry, to make this be more less confusing. So now that we found the arrows, let me get rid of them for a second. I'll just keep one or two. just for illustrative purposes. But you see, like when you slice the sphere with this plane, you get some sort of curve. Which is the blue curve that I'm trying to draw. Can everyone see it? And that's how much your shadow can go into on the XY plane.
So would it be kind of like the arc length of that?
Well,
The projection of that arc length onto the X and Y plane?
it will, how can, like, here's what you should think about. How do you find, maybe it didn't help that let me do some fewer vertical arrows.
I have a question for illustration. Would it help to make the segment of the sphere that's outside of our bounded region in like dotted lines rather than solid brown?
Well, the solid brown really aren't, I mean, they don't make that much of a difference in this case. What you should realize is that like the algebra picture is a little bit better. Let's just go first there. What I'm saying is that there's like, does everyone see it? Like there's sort of like this curve that you get where the plane hits the sphere.
So then would the shadow be bounded by, say you dropped a height line from this intersection of the plane and that curve?
Basically what you do is like the idea is that you find like that curve and then you just drop like a parallel.
Yep.
From there, like imagine the paint dropping, right? So you just forget about the height of the curve and then like you just get some points on the XY plane.
Yeah, okay.
Yeah, like so like, but like we just need to take it a step at a time. So where does this intersection happen? They happen when the equations are the same, right? Like, an intersection between, how do you, like, let's do like let's do an analogy first, right? Like if you had wanted to find, just, I will erase this in a second, but if you want to find when the parabola intersects y equals x, right? What you do is set the two equations equal to one another, right? And that's how you get x squared equals x or x equals 0, 1, right? That's when two curves meet. So if you want to find when two surfaces meet, which is when this plane meets the sphere, you have to set the equations equal to one another. And thankfully, they are both already written in terms of z. So you can just set the equations equal. So you get what's the intersection of the plane with the sphere? Well, that's when root of 1 minus x squared minus y squared equals y. Is that making sense? Because that's like the formula for z in both cases. Right, so you square both sides, so you get 1 minus x squared minus y squared equals y squared. And so you get 1 equals x squared plus y squared plus 2y squared. Is that okay?
That would be the intersection.
That would be the equation, yes, of the intersection. Could we also set the equation equal in the other example? Well, yes, although I do think it's better to try to draw them out in general. Right, but if you think of in terms of x and y, what would that, I mean, if you just thought about this as an equation for x and y, what would that be correspond to? Anyone recognizes this equation for x and y? It's almost a circle. It's like an ellipse, right? So like there's some ellipse here going on, which is, let me draw it below. So this is like part of the ellipse 1 equals x squared plus 2y squared, right? And what we're saying is that above each point of the ellipse, you see like a corresponding point on this like line of intersection. Is that making sense? So by setting like the two equations equal to one another, like we sort of realize that the shadow is determined by an ellipse. In fact, I don't know. Allow me to show you the intersection. I think this will help. So let me go for a second back to GeoGebra and I'll finish this in a moment. So this is the curve, which is cosine of t square root times sine of t, and then square root times pi over 4. Let's see. Oops. Z equals y. Oh, it's like it's divided by 1 over. I think this should be fine. Pi over 2. Do you see it? Do you see the intersection? It's like this black curve. That you see. Let me do it even thicker. And so I'm saying that if you look at the shadow of this curve on the XY plane, is essentially like the boundary of the ellipse, like the part of the ellipse. So you're just that's where the shadow ends. So because here you have x squared plus 2y squared equals 1. And that's this is not going to, I mean, it's an ellipse, but like now if I wanted to draw this on GeoGebra, it would be a little bit more complicated. So
can you view it from straight down, like from the z-axis down onto the xy plane?
right. Yeah, that's a good point. I mean, yes, I should be able. I mean, it doesn't like now it's not too great, but like you should like if you
No, that helps.
yeah, you should sort of see like the perspective that is like an ellipse. So just to finish this up, let's go back to the picture. So the takeaway is that the shadow is determined by this ellipse region. So you have, I mean, you only care about the part of the ellipse on the first quadrant. So this is like 1 plus x squared plus 2y squared. And so again, if you wanted to find the bounds for the shadow, you just like in this order of integration, you use the dy dx order. So you're using vertical arrows. And so now you have to solve the equation of the ellipse for y. So you can say that 1 minus x squared equals 2y squared. And so 1 minus x squared over 2 equals y squared. And so the bounds for the ellipse are from y equals 0 to square root of 1 minus x squared over 2. And for x goes from 0 to 1. And so those are the bounds for this region of integration in Cartesian coordinates. Is that making sense?
Well, most of our problems involve that intermediate step of needing to find the shape of the projection.
Yeah, usually need to find the intersection between the and many ones. Yeah, you do have to do that.
Okay.
Yeah, good. So next time, and this will keep reappearing. So next time we'll still continue doing triple integrals, but we'll go into the ones that are called cylindrical coordinates. So that's like the version of polar coordinates for 3D regions. So we will discuss those next time. Okay. I'll see you on Thursday.
Thank you. Have a nice day.
Bye. Bye.